Okay, so here we go. I will talk about those theories related to the experiment, but the detailed experiment and the apparatus, I will talk about it in the video. Okay, next week I will post. So the following 2 weeks. Today, at the end of the lecture today, I will give you a safety quiz. Okay. Uh, Initially, I plan to give all 3 safety quiz today, but I'm thinking maybe not. Okay. Let me give you just one safety quiz today, which related to the refrigeration unit, the safety, so and all those kind of things. Only 6 multiple choice questions. If you review the handout I give you, you shouldn't have problem. Okay, and also a couple questions about the operation of the refrigeration system, which I showed you in the video. Okay, so that's a plan. So how we do it? I'm going to, you have GroupMe, right? I'm gonna send the quiz through GroupMe. Okay, you take a look, and you can either write on your iPhone. You can write ABCD on that sheet I send it to you, or you can, if you cannot do it, then you can just write on your own paper ABCD whatever for the 6 question, then post it in Moodle. Take a picture and post it in Moodle. Okay, so it will be super easy. Maybe take 2-3 minutes for you. Okay, so okay, I still have a couple of people joining. Hello, can all of you, the 2 of you just joining, can you hear me? I just talked about the plan today. I'm going to talk about the theory of the next 2 experiments, and I will post experiment videos, virtual experiment videos next week and the week after next week. Okay, so, and also we will do a safety quiz at the end of today's lecture. Okay, take you probably less than 5 minutes to do. I will send the quiz through GroupMe, our group. Okay, then you can just write your answer on the paper, take a picture and send it back. I'll post submit through Moodle, or maybe you can just write the answer on a separate sheet. It's fine. Okay. Okay, let me share my screen. Let's look at the next 2 experiments. Cross-flow heat exchanger. Okay. Can you see it? Okay. This is the apparatus. Oh, by the way, when we take the quiz at the end, please turn on your video. Everybody, let me see your face on the video. Okay, that's all I needed. Okay. Okay, this is the apparatus for the cross-flow heat exchanger. Okay, so there's a square duct. The main thing here is a square duct. Actually, I can write on it. Hold on. This portion is the main flow chamber. Okay, it's not round duct, it's a square duct, but it's okay. It's a blower here. Okay, it's a blower, like a fan. Okay, the creates airflow from bottom to the top. Okay, so you have a heat transfer unit inserted into the air duct. Okay, this unit is connected to the monitor, to the monitor here. So it's an electrical heater. Okay, this thing, the whole thing is an electrical heater. It's a monitor. It can show the temperature. It can adjust the voltage. Electrical heater. So the power wattage is equals to voltage times the current, right? Or equals to V time divided by V squared over omega, right? Is that right? Okay, so it's a heater, right? So the voltage you can adjust. This switch here, okay, you turn clockwise, it had a high voltage, turn counterclockwise, had low voltage. So this I think I can use Q to represent the total heat generated from the electrical heater. Okay, so the resistance is given is 70 ohm for the resistance. So based on the voltage you adjust it, you can actually calculate the total heat generated from the electrical heater. And the heat will go through the cylinder unit, and it will hit the surface of the cylinder unit. So the total heat transfer, total heat generated to the cylinder can be calculated by this, and it will be transferred into the surrounding air. The airflow is going around it and carry the heat away. Okay, so this is the heat balance. Total amount of the heat transfer Q goes to the air is equal to the total amount of the heat generated by the electrical heater. Okay, so this is, any question here? Is that clear? Is my drawing here? Okay, so think about it. The surface is hot, right? So the wind blow to it, it will carry the heat away. So the surface temperature will be cooled down a little bit, okay, because of the convection heat transfer. Okay, how about the heat transfer rate from the surface to the air? It will be equals to convection heat transfer coefficient times the surface area times T surface minus T infinite. Okay, is that right? This is the convection heat transfer equation. Is that what we learned in the heat transfer class? Right, so in this lab, you are going to find the H. Okay, so surface area is given. Okay, I think in the handout it gives. Okay, somewhere in the handout. Surface temperature and ambient temperature is measured. See, on this monitor here, okay, it will show the surface temperature and ambient temperature. Ambient temperature is a constant, it doesn't change. Okay, during the experiment. I think I run the experiment probably 20 minutes for this lab. So during that 20 minutes period, we can assume the ambient temperature is constant. And indeed, it is constant, about 21, 22 degrees. Okay, but the surface temperature changes. That's what you control. Okay, that's the voltage what you control. Okay, your voltage is higher, then the Q is higher, then the surface temperature could be higher, right? Okay, so I want to calculate this based on this, so you can measure. The monitor here will display the TS and the TN ambient. Okay, so only thing you need to know is the Q. The Q is equivalent to the electrical heat generation. So the voltage here is showing on this panel. There's a needle here shows the voltage. Okay, the resistance is given. So at any setting, any voltage setting, okay, in any voltage setting here, you can have V square over 70 ohm. Then you can, this is the wattage, the heat generated. It's equal to the heat transfer, convection heat transfer. Okay, so you have the area, you measure the surface temperature and the ambient temperature, so you should be able to calculate the convection heat transfer coefficient. Okay, is that clear to everybody? That's any given moment, any set wind speed. Okay, so you know the convection heat transfer coefficient change with the wind speed. Is that right? How does it change with wind speed? Is it proportional or inversely proportional? It's the wind below, it's the wind is stronger. Is your H bigger or H smaller?
Is it bigger?
Of course, right? Yes, you're right. It's bigger, right? So, you know, it's H is dictated by how fast the wind. I set it up here. So the next stop is this. Now, this at any given wind speed, you can find your H based on this relationship. Okay, so in this experiment, I'm gonna change the wind speed 6 times. Okay, I'm gonna change the wind speed 6 times. So you will have 6 convection heat transfer coefficients. measured. Okay, then I want you to produce a plot and use what? Do you remember? What is a Nusselt number? Nusselt number or Nusselt number? It's just H. Okay, it's a dimensionless H. Okay, no unit. Okay, so I'm expecting to see something change like this. When the flow rate increases, your heat transfer coefficient increases too. Okay, I think you have 6 readings. So you can actually create a curve like this. Okay, I give you 2 correlations. Okay, previously validated correlations from other researchers or engineers in the world. Okay, so I want you to also plot the 2 correlation. I give you the equations. Okay, Nusselt number versus. I'm sorry. I do Q here, but eventually I want you to do Nusselt number versus Reynolds number. Same thing, right? Reynolds number is from velocity. Velocity diameter divided by viscosity, basically related to the Q. The relation is still like this. Okay, Nusselt number versus Reynolds number eventually. Okay, so that's the next experiment. Okay, let me show you some detail on the handout. Okay, this is the same drawing. I think okay, here, I want to show you the equation I gave you. Okay, this is the equation I'm talking about, convection heat transfer equation. Okay, from the surface, cylinder surface to the air. Okay, and equal to the same Q, the electrical heater. Okay, voltage squared divided by R. This V here is the voltage. Okay, it is not the velocity, voltage. Okay, so the voltage is on the panel. You can actually control the voltage, right? Velocity, you need the velocity because you need the Reynolds number, right? Okay, Reynolds number, velocity, D, viscosity, right? There's a correlation here from the machine. Okay, based on the H is the manometer readings on the panel, on the machine. Based on the reading value, the temperature, this is the absolute temperature. I'm sorry, this is the temperature K. Okay, then this is the pressure, atmospheric pressure, absolute value. Okay, so based on this correlation, you can find the velocity. Okay, I'm going to change the blower 6 times, so you have 6 velocity. You have 6 pressure readings, so you have 6 velocities. Okay, so you have 6 Reynolds numbers. Okay, diameter, everything's given. Okay, from this. So the Nusselt number is here, from H times diameter divided by K. Okay, K of the air. Okay, so that's the Nusselt number. So then you should be able to create Nusselt number versus Reynolds number. Okay. Then I think there's 2 correlation I give you on the next page, 1 and 2. Okay, I can show it bigger. Okay, look at this Reynolds. The first equation, equation 6, is Nusselt number equals to. It's very simple. It's just Reynolds number. Okay, in the right hand side. So Nusselt number is strongly related to Reynolds number. The second equation, you have Reynolds number. You also have a Prandtl number, and the viscosity of the air over viscosity at the surface temperature. Both of viscosity are the air, right? Okay, but viscosity changes with temperature significantly. Okay, so at the ambient temperature, air has a certain viscosity. At the surface temperature, if you use different temperature, you have 2 different viscosities for the air. Okay, it needs the ratio, okay, to be included in this equation. So these are the 2 existing correlations. So you can just simply plot Nusselt number versus Reynolds number. When you're putting different Reynolds numbers, you can plot this line. So these 2 lines are really close. Okay, but I want to see your measured. You have 6 different measurements. Okay, I want to see your measured curve, how close to the existing conditions, existing correlations. Okay. Is it clear to everybody what we need to do? This is the most important lab for the semester. Okay, because this lab is selected for the ABAT evaluation. Okay, whatever you do we will record it and we will save it and we will send it to ABAT for them to evaluate for the entire class. So this is the lab. Okay, and this is a good lab because you have a correlation to compare with for your experiment. Think about the refrigeration cycle experiment. We have nothing to compare with, right? I don't have, you basically, that's what you measured. Here, this is what you measured. You have the comparison, okay? You have the correlations. They can tell, you can tell if your measurement is good or not. Okay, so any questions on this one? Okay, again, here is basically 6 different velocities. I set the blower 6 times, so you have 6 different velocities. You have 6 different Reynolds numbers. But how do you generate these correlation curves? Use the same 6 Reynolds numbers, plug into these 2 equations. Okay, you get the Nusselt number curves for the same 6 Reynolds numbers as you do in the measurement. Okay. I think all the quantities are given in the handout. This is, see that the surface, total surface area is given. Okay, the diameter is given somewhere. The pressure value for this equation is also given. And the pressure reading, H, will be on the data sheet. I will give to you. Okay, so, and oh yeah, one thing is during the experiment, look at the equation we did here. T surface and the T infinite. T infinite is always the same. Okay, so in the experiment, I purposely keep the same surface temperature for all 6 different flows. Oh, you guys think about, hey, if I increase the flow, the surface temperature is going to drop, right? How do I maintain the same surface temperature? The way I maintain surface temperature is I increase the voltage. See, I increase the voltage. Okay, you have a bigger Q. You have a bigger Q. Although the Ts and the T infinite are all the same for the 6 measurements, then you have a bigger Q if the flow is stronger. Then your H is bigger. Everything else is the same. I'm purposely make A, of course, is the same. And the Ts and the T infinite are all the same for the 6 measurements. Okay, so your H basically is proportional to Q. If the Q increases, the voltage increases, your heat transfer coefficient also increases. Okay, the key is I maintain the surface temperature be the same. Otherwise, if I turn on the blower stronger wing, then the surface temperature is going to drop. Okay, I have to supply more heat to it to maintain a same surface temperature. Okay, is that right, everybody? Is that clear? I want everybody to do well on this lab. Okay, you're the face of our program, at least for the experiment part. Okay. Okay, I guess that's it. Don't worry about the data sheet. Data sheet has the A data, but you only need the 6. I think I only did the 6. It takes very long to do the measurement, actually. So these are the requirements for the lab. Okay. This is number 4, right? Number 4. Okay. The next one. Let me.
Dr. Zhang, can I ask you a question real quick?
Yeah, sure. Go ahead.
You said for equations 6 and 7, for the other 2 and 3 Reynolds numbers, those are just to compare to the.
So any experiment, I want to add this. Any experiment you do, how do you know it's good? Yeah, you have no way to prove that you're doing a good job until you compare to other people's research. They already did exactly the same thing before. Okay, these 2 equations basically is from other groups. You know, it's a long time, 20, 30 years, but it's the same experiment they did. And they conclude to this correlation based on their measured result.
So when we measure, we're using the first Reynolds number, and for when we plot on the new Salter Reynolds number chart, are we using equation 4?
Okay. When you do measurement, forget about 6 and 7 equation.
Okay.
Okay. 6 and 7 is not your measurement. That's what other people did.
Okay.
Okay. That's for your comparison. But what you really do is for doing this equation and this equation. These are the equations you are going to use to measure your heat transfer coefficient. Okay. Your voltage divided by resistance is your heat transfer rate. Your heat transfer rate become HA delta T. Okay, HA delta T. So if I know a Q, I know a delta T, I know A, I can calculate my H. Okay, that's 1 point. So I change the wind speed for 6 times. I'd have 6 different Q, H, 6 different Qs, yes. Okay, so that's how you measured Reynolds number versus Reynolds number. Okay, so after you do the curve, now comparing it to the existing correlation. Okay, that's what you need to do. Okay, you have 3 curves. Basically, I want you to produce the thing. Like 2 curves from other people, 1 from you. Okay. Good. Any other questions? Okay. Let's look at the next one. Next one here. So next one, I want to show the picture. Now, the previous one is a smooth tube. Okay. Now you look at the fin tube. You know, you're adding fin to the tube, then you increase the heat transfer, right? The cross-flow heat exchanger always has fin on it, mostly. Okay. So this time it's the fin bundle. It's not just one tube. For the smooth tube, just 1 tube, nothing else, just 2. This is the fin tube bundle. Okay, more realistic. Okay, so we want to see the heat transfer performance on those different locations, 1, 2, 3, and 4. Okay, so the wing is from the bottom, right? From the bottom to top. Okay, I can't put my pen on it. Okay, just let me explain. So wing is from the bottom to top. So on each of the position, obviously there's a slightly difference in the heat transfer. Okay, educated guess which one has a better heat transfer?
Closer.
The bottom one, or the middle one, or the top one?
The bottom.
Okay, so your first guess probably is bottom because it's exposed to the air. But think about it. When the air goes through this bundle, remember the conservation of mass, remember? Conservation of mass, right? The flow rate has to be the same when it goes through this bundle. Okay, flow rate is velocity times the area. Okay, think about the inside the bundle, the area is tiny. When the same flow rate gonna go through it, the velocity is very high. Okay, the convection heat transfer coefficient is actually from the velocity. Okay, the faster the velocity, you have higher heat transfer. Okay, heat transfer coefficient. Okay, so it might not be. Let's test the 4 position. What is the heat transfer for the 4 position? Okay, then let's put into the same picture to compare. So in this lab, let's do something slightly different. We do, let's plot the heat transfer, heat flux. This is phi equals to heat transfer divided by area, right? The rest of the equation are the same as the previous handout. We only added this phi equation. So phi heat flux, right, equals H delta T. Okay, so it's basically similar situation. You have the surface temperature, shown on the panel. You have the anti-ambient temperature. Okay, so for this unit, so of course, you only can see the surface temperature on the unit, right? This is the active unit. See, the bottom one is the active unit. Okay, we can switch positions. So it will show only the surface temperature on the active unit. So you can calculate the heat flux for the active unit. Okay, based on equation 4. Okay, so for this time, we don't change the wind speed. We set the wind speed constant. Okay, we set the wind speed constant. So, but what we change? We change the surface temperature. With the constant wind speed, I can turn on the voltage, make it the surface temperature hotter, right? Or I can turn down the voltage, make the surface temperature cooler, lower, okay? So based on this relationship, since the wind speed is the same, so H is the same, okay? H doesn't change. So your heat flux is proportional to the temperature, surface temperature. If the surface temperature is higher, your heat flux is higher. Okay, from the handout, you will see I just want you to plot phi versus delta T. So on each position, let's change 4 different surface temperatures. Okay, change 4 different surface temperatures. So you can, let me still write it down. I think I need to write it down for you. Okay. Switch my, what? Wrong window. Okay. Let me write it to the end, at the end of it. Okay, so for this lab, I want you to okay. I'd like you to put, why I cannot write on it? Oh, yeah. Okay, for some reason I can't write down the last page. Okay, so the equation is this: phi equals to h Ts minus T infinite. So this is Ts minus T infinite. This is phi, okay? There will be 4 points, 1, 2, 3, 4, okay? You change 4 different voltage. So you have 4 different surface temperature. Ambient temperature is a constant, okay? 4 different surface temperature, you have 4 different phis, okay? So on 4 different locations, now this is the one position of the thing, okay? Oh, by the way, you say, how do you find the phi, right? Phi is what? Phi is just Q divided by area, right? Q, hey, we already have it, right? Q what? From the voltage. Again, or your total heat transfer rate basically is from voltage in the next 2 experiments. Okay, you have it. Based on the voltage reading, you should be able to know what is the total heat transfer rate. Is that right? So, okay, you switch the voltage for 4 times. Okay, you have 4 different voltage, you have 4Q. Q divided by area is phi. So you know the phi. So based on this Ts minus T infinite delta T value, each delta T value, you should have a phi. Each delta T, you should have a phi. Each delta T, you have a phi. Okay? So you can have a plot, have a straight line for one position. Now you switch the active unit position to the second position. You have another line there. I don't know, it's above or below. So eventually you have 4 lines here. 4 by 4, total 16 readings. Each position have 4 readings. Okay, total 16 readings for 4 curves here. Now you can compare. So based on this for example, if you have a 4 lines like this, which one has a better heat transfer? Of course, the top one. For the same delta T, you have a bigger phi, bigger Q, right? You have a better heat transfer. That can tell you actually which position is the best, which position is the worst. Okay, that makes sense? I don't know. I don't want to tell you now which position is good. Okay, let's find out from the report. Okay. Also, I want you to compare one curve, put one more curve there. That's a smooth tube. But you don't measure smooth tube in this lab, right? You just compare with smooth tube you did in the lab number 4, right? You're supposed to know the heat transfer coefficient for the smooth tube. Okay, for the same 4 delta T, you should be able to calculate the phi for the smooth tube and plotted an actual line here. Okay, actual line tells you that it must be below. Okay, it must be below. Okay, because thin tube, of course, has a better heat transfer than the smooth tube. Okay, but be careful. You need to find the H for the smooth tube with the same flow condition, which means you have the same Reynolds number. Okay, the Reynolds number range for the lab 4 will be actually at the higher velocity range. Okay, this velocity in the lab number 5 is lower than the lab number 4. Obviously, because of so many bundles, thin tube bundles, the velocity is slower. Okay, so how do you get the H for the smooth tube? Okay, let's make it a little bit easier for you. You can use 2 correlations, equation 6 and 7, just one of them. Okay, putting a Reynolds number, then you will find your Nusselt number. Okay, you will find your H for the smooth tube. Okay, but the reason is I want you to place that smooth tube curve there to show that actually your thin tube is way better than the smooth tube in heat transfer. Okay, so that's the lab number 5. So these are the 2 labs for the cross flow heat exchanger. Okay, so it's basically we review the knowledge of convection heat transfer. Okay, I guess that's it for my lectures. I will give you a more detailed video on how we operated for the both labs next week, okay, and then the following week, okay. So watch the video and you can do the lab report, okay. Now, let's do the quiz quickly, okay. I don't want to take too much. But by the way, any questions before I close this? Good, is that clear? I think these are 2 good labs, okay, very good lab to verify, to review your heat transfer knowledge. Okay, now let's do the quiz. Turn on your video. I'm sending the quiz problem in the group me. Okay. Okay, it's there. Only 6 questions. Whatever you want to do, you can write down your iPhone, or you want to print it and then write down with paper, pen, or no, it's up to you. Okay, or you just want to give me a answer 1, 2, 3, 4, 5, 6 problem A, B, C, D. Separate the paper, write the answer, take a picture, submit to Moodle. Okay, go ahead. And if you've done it, you can go.